Welcome to lecture number 36. We are studying circuit analysis and today we'll solve an example related to related to Norton's theorem. Right. I'm solving this example on the request of a student. Here is an example that I'm going to solve using Norton's theorem. We are required to find this output voltage V out using Norton's theorem. So the step number 1 is we have to remove ZL and replace with a short circuit. So we'll remove ZL, that is 1 ohm resistor, and we'll replace it with a short circuit. Now we are supposed to find the current through this short circuit path. We call it ISC. In order to find this current, either we can apply loop analysis or a nodal analysis. If we apply nodal analysis, we have to write only one equation. So let's opt nodal analysis. Assume a voltage V here. The other node, this node is the ground node. So the current in this branch would be, we'll assume it to be moving away from the node because we don't know its exact direction. V minus 10 at an angle of 0 divided by 1. Even in this branch, we'll assume it to be moving away because we are not sure about its exact or actual direction. And even in this branch, we'll assume it to be moving away. So we have written KCL equation for the only node in the circuit, right? Since let's further simplify this. 10 at an angle of 0 can be written as 10. Anything in denominator, if we have a 1, that is actually the numerator. Minus 1 over j is minus j v1. 1 over j is minus j, minus times minus is a plus. j1v is equal to a 0. So we come up with V is equal to 10 volts, but that is not the required quantity. We have to find I through this branch, and we'll call it ISC or I short circuit. This I short circuit can be computed by dividing this V with the impedance of the branch, that is minus J1. So 10 over minus J1. That is minus 1 over j is minus j, minus times minus is a plus. So this becomes j10, or we can write it 10 at an angle of 90 amperes. That is step number 2. Step number 1 was to replace this, to remove the load and replace it with a short circuit. Step number 2 is to find ISC. Step number 3 is find Z Thevenin. But first, replace this short circuit with an open circuit. Find the Thevenin here and replace sources with their equivalent impedances. The equivalent impedance of this only source, that is the voltage source in this circuit, is 0 ohms. So it's replaced with a short circuit. So now we are ready to compute Z Thevenin. Right, to compute Z Thevenin, we see these two impedances, 1 ohm and J1 ohm, are in parallel. So Z1 Z2 times divided by Z1 times Z2 divided by Z1 plus Z2. This is exactly the same that we have been doing for DC analysis, where we have two resistances and we write R1 R2 over R1 plus R2 as the equivalent resistance. But here we have, instead of R's, we have Z's, Z1 times Z2 over Z1 plus Z2. And then we have this minus J1 in series with this parallel combination. So if we multiply, this one becomes J1 minus this J1 times 1 plus J1 over the LCM 1 plus J1. 10 at an angle of 90 is ISC. We have to remember that because we have erased that value. Right, so Z Thevenin is J1 minus J1 minus J squared, and we know J squared is minus 1 divided by 1 plus J1. So this cancels 1 over 1 plus J1, or 1 plus J1 is square root of 2 at an angle of 45. So it can also be written as 1 over square root of 2 at an angle of minus 45. When this angle 45 is taken into the numerator, its sign flips. So Z Thevenin can be written in rectangular form like this and polar form like this. So now we are ready to perform the last step, that is to make equivalent circuit and put the load back. We have to, what is Norton's equivalent? A current source having magnitude ISC, and we computed ISC to be 10 at an angle of 90 degrees. And then we have this Z Thevenin, and Z Thevenin is 1 over 1 plus J1. We have just computed 1 over 1 plus J1, or 1 over square root of 2 at an angle of 45. And then we have to put the ZL back, which is 1 ohm, and we are supposed to find voltage drop across this load. Right, this is our unknown quantity. This is the required quantity. Right, so to find V out, we have to first compute current through this 1 ohm resistor. That we can obtain by applying CDR, current divider rule. We'll put this in numerator, 1 over square root of 2 at an angle of minus 45 divided by 1 plus the same. Write it in its rectangular form because we have to add a 1 to it, therefore it is more convenient form. Right, and then 10 at an angle of 90. And once we solve this, we reach to an answer that is 2 times square root of 5 at an angle of approximately 64 degrees. So solving this is left as a homework for students. It's straightforward. That is I0 amperes. And finally, we need to compute V out. V out is the voltage drop across this 1 ohm resistor. We already know the current flowing through it, so V out should be the current flowing through this 1 ohm resistor times this resistance. This is according to Ohm's law. So this is 2 square root of 5 at an angle of 64 multiplied by 1, which is 2 square root of 5 at an angle of 64 degrees volts. The same. So in our lecture, in our next lecture or next 2 lectures, we'll solve the same problem using nodal and loop analysis, and we'll reach to the same answer. Thank you.